Ever wonder how your phone's GPS knows exactly where you are? Or, how ancient sailors crossed vast oceans with nothing but the stars to guide them? Well, it all comes down to this incredible, invisible grid that wraps around our entire planet. And today, we're going to crack the code on that very system, latitude and longitude.
All right, so here's the game plan. We're going to start with a big why, like why even bother with a grid in the first place? Then we'll break down the two key players, the horizontal lines, latitude, and the vertical ones, longitude. After that, things get really cool. We'll uncover this wild connection between longitude and, believe it or not, time itself. And to wrap it all up, we're going to take a little trip across the international date line. It's a real mind-bender.
Okay, let's just dive right in. So the first, most basic problem is, well, it's a huge one. How in the world do you give a unique address, like a street address, to any single spot on a giant, spinning ball? It's a puzzle that people wrestled with for literally centuries.
No, seriously, just stop and think about this for a second. Imagine you're out there smack in the middle of the Pacific. No street signs, no buildings, no landmarks, just water. As far as the eye can see. How do you tell anyone where you are? It feels totally impossible, right?
Well, the answer, and it's a brilliant one, is this elegant global grid system. These imaginary lines we talk about, latitude and longitude, they're basically Earth's coordinate system. Think of it like a web that covers the whole planet, letting us pinpoint any location with just crazy precision. From the tippy top of Mount Everest all the way down to the bottom of the Mariana Trench.
All right, so let's actually build this address system one piece at a time. We'll start with the first half of that address, the horizontal lines. You'll also hear them called the parallels of latitude.
The absolute key word to remember here is parallel. These lines of latitude are just imaginary circles running east-west, and they never, ever meet. They're always parallel to the equator. They tell you how far north or south you are from that big starting line.
Now this is where it gets really interesting, because you can see the greatest hits of latitude lines right here. Of course, you've got the equator right there at 0 degrees. Then you have the tropics of Cancer and Capricorn at 23.5 degrees north and south. And way up and down, you've got the Arctic and Antarctic circles. But are these just random lines on a map? Absolutely not. These lines are what define the major climate zones of our entire planet.
So, what are the main takeaways for latitude? A few key things. First, every single one is a complete circle, but they get smaller and smaller the closer you get to the poles. The equator is the big one. It's the only one we call a great circle. And here's a really cool fact to file away. The distance between each degree of latitude is always the same, 111 kilometers. Super consistent.
Okay, so we've got our north-south position totally locked in. We're halfway there. But to get a real pinpoint location, we need the other half of the address. So let's talk about the vertical piece of this puzzle, the meridians of longitude. Now these are totally different from latitude. Instead of full circles, lines of longitude, or meridians, are semicircles. They all stretch from the North Pole all the way down to the South Pole, and they actually meet up at the top and bottom of the world.
So, the equator makes perfect sense as a starting point for latitude. It's the middle. But for longitude, well, there's no natural middle. They had to pick one. And after a lot of debate, the world finally agreed on the Prime Meridian, a line that runs right through the Royal Observatory in Greenwich, London. That line, at 0 degrees longitude, became the official starting point for measuring everything east and west. A decision that, honestly, changed global navigation and timekeeping forever.
Okay, this little chart is perfect for summing it all up. Let's just quickly run through the big differences. On one hand, you've got latitude lines. They're complete circles, and they're always parallel. On the other hand, you've got longitude lines. They're only semicircles, and they all meet up at the poles. And the spacing. For latitude, it's always that same 111 kilometers apart. But for longitude, the lines are spread way out at the equator, and then they bunch up tighter and tighter until they're literally touching at the poles.
So, there you have it. We can now find any spot on Earth. That's pretty amazing on its own. But what if I told you this grid does something else? Something you could argue is even more powerful. Because this grid doesn't just measure space, it also measures time.
Okay, so how does that work? Well, it all starts with something super simple, a circle. And our planet Earth has 360 degrees.
And we all know it takes 24 hours for the Earth to spin around one full time on its axis.
So, here's where the magic happens. You do some simple math, 360 degrees divided by 24 hours, and what do you get? 15 degrees. That's it. That simple number is everything. It means that every single hour, the Earth rotates 15 degrees of longitude. And folks, that is the bedrock of all of our global time zones. And this diagram just lays it out perfectly. Look at the Prime Meridian there at 0 degrees. Let's say it's noon. If you move 15 degrees to the east, boom, it's 1 hour later, 1 p.m. Go 15 degrees to the west, and you go back an hour, to 11 a.m. It's really that simple. The entire world's clock is literally set by longitude.
So the rule of thumb is easy to remember. The Earth spins towards the east, right? So places to the east of Greenwich get the sun earlier, so they gain time. And places to the west get the sun later, so they lose time.
And hey, just a quick reminder about latitude's other superpower. The way the sun's rays hit the Earth at different angles because of latitude is what gives us our big climate zones. You know, the hot tropics near the equator, the milder temperate zones, and of course, the freezing cold polar regions.
All right, we've pretty much circled the globe, but our journey is not quite over. For our last stop, we need to go to the exact opposite side of the world from Greenwich to a very strange, almost magical line where today literally flips over and becomes tomorrow.
This, my friends, is the International Dateline. It's the 180-degree meridian, and it's where the calendar day officially changes. But you'll notice it's not a straight line at all, is it? It zigs and zags all over the place, and there's a good reason for that. It's carefully drawn to avoid cutting through any countries. Could you imagine the chaos if one side of your town was on Tuesday and the other was on Wednesday?
And now for the really mind-bending part. It's basically a form of time travel. When you cross this line, you either gain an entire day or you lose one. So check this out. If you're flying west, say from the US to Japan, you cross the line and you completely skip a day. Poof, it's just gone. But if you fly the other way, east, from Japan to the US, you cross the line and you go back in time. You actually get to live the same day all over again.
And this quote just sums it all up so perfectly. It really captures that elegant mathematical link between the physical shape of our planet and how we even think about time. At the end of the day, this grid isn't just about where you are, it's also about when you are.
And all this leaves us with one last really fascinating question to chew on. You know, we built this whole system of time zones for a world of steamships and railroads. But we live in a world of instant global connection now. So how might our idea of time itself have to change next? Thanks for digging into this with me.